let's get some motivation for semi-definite programs before we actually jump into them. So remember this linear program formulation, right, where I was minimizing a linear function subject to linear inequality constraints and linear equality constraints. Semi-definite programs are born out of the idea, and actually really conic problems in general are born out of the idea of changing this less than or equal to sign to a different kind of ordering. So the orderings that we're going to do are called partial orderings, because you can't always compare any two elements. But that's the idea. So let's just get a bit of details for SDPs, and we'll start making sense. Just a bit of a recap of some of the notation that we've seen. Sn is the space of symmetric n by n matrices. If I write a plus subscript, then that denotes the set of positive semi-definite matrices. So these are matrices that are symmetric n by n matrices that have all their eigenvalues bigger than or equal to 0, or equivalently, U transpose x times U is always non-negative, no matter what I put there for U. So that's a semi-definite matrix, recall, which we write as we write this as x squiggly bigger than or equal to 0. So that means that x is an n by n positive semi-definite matrix. And then Sn++, so two pluses in the subscript, is the space of strictly positive definite matrices. So they have all the eigenvalues strictly larger than 0, not just bigger than or equal to 0. And that means that they satisfy this positive definiteness inequality strictly, not in a non-strict sense. So for all U that are not 0, U transpose xu is strictly larger than 0. Yeah?
Is there a reason that you're explicitly calling out that the 0 matrix does not belong to the set?
No, the 0, well, so I'm saying that the U can't be 0. Right, because if 0 transpose x times U is always going to be 0. Right. So some basic facts from linear algebra. I just said these out loud, but here they are formulaically. If a matrix is symmetric, then, well, actually, I didn't say this one, but this is a basic fact from the spectral theorem for matrices. If a matrix is symmetric, then its eigenvalues are going to all be real. It's going to have all real eigenvalues. If a matrix is symmetric and positive definite, semi-definite, then all its eigenvalues are going to be non-negative. So we write that as lambda x is an Rn plus. So lambda x denotes the set of, I should have maybe made that notation clear. Lambda x is just the set, it's the vector of eigenvalues of the matrix x. And if x is n by n, then I think of this as an n-dimensional vector. There could be ties here sometime, right? Or some of these could be 0. But I can always think of it as an n-dimensional vector. So this is just a nice kind of way of summarizing those facts. And if x is strictly positive definite, then its eigenvalues are all strictly positive. So it lies in Rn++. We can define the inner product over the set of symmetric matrices as follows. It's often denoted by these brackets. So x triangle bracket y, or x dot y, but the dot we usually put as a dark circle. So this is like an inner product over the usual L2 inner product over vectors. In fact, it's the exact same thing. It's just the sum of xii times yii. Xij times yij over all I and j. So it's what happens if you were to string them out into vectors and take their inner product. But I can write that more concisely as the trace of xy. So just if you haven't seen that before, then just write out what the trace of xy is, and you'll see it's just the usual inner product had we unraveled these matrices into vectors. Okay, so now I have an inner product space over matrices, and I'm going to define a partial ordering over symmetric matrices, sometimes called the Launer ordering, but we're just going to always use this ordering, so that name is not necessarily important. And if you give me any two symmetric matrices x and y, then I'm going to write x is bigger than or equal to y, if and only if x minus y is positive semi-definite. So we've already used this a bunch of times, but I'm just defining it formally. Okay, it means that the eigenvalues of x minus y have to all be non-negative. All right. So now we can define an SDP. And it's really very much like a linear program. In fact, it's exactly like a linear program, except I've just changed the meaning of that less than or equal to sign. I've overloaded it with a different partial ordering. So an SDP you can think about as a problem where the optimization variable is x, the criterion is C transpose x, the constraints are that AX equals B, everything you know from linear programming, but the inequality constraint changed. And I'm given matrices now, F1 through Fn, which are symmetric matrices. Say in d by d symmetric matrices. And I'm giving another matrix F0. And I'm saying that the matrix given by x1 times F1 plus x2 times F2 all the way through xn times Fn has to be less than or equal to the matrix F0, meaning that F0 minus the matrix on the left-hand side has all non-negative eigenvalues. That's what it means, right? That's what that ordering means. So for linear programs, for the LP world, we had this constraint, right? And if I write out the columns of D, if I write the columns of D as, let's say, dj, then this is what I've asked for equivalently. So these are the columns of D. For SDPs, I've just replaced each of these dj's and this D with a matrix. That's all I've done. So I've called them F. And now I say matrix less than or equal to, according to our order of matrices, another matrix F0. OK. This is always a convex optimization problem, no matter what F1 through Fn and F0 are. And we learned that last time, because we learned this is called the linear matrix inequality. We learned that these kind of inequalities always are convex constraints on X. It doesn't matter whether or not F1 through Fn are themselves, say, positive semi-definite. As long as they're symmetric, this is always a convex constraint set. So as I write an SDP in this form, it's always a convex problem. I claim any linear program as a semi-definite program. So I claim now that SDPs, I'm giving you this part of the hierarchy. This we're familiar with, because you just take the Q matrix to be 0. I'm claiming that SDPs contain LPs. So how do we see that? In fact, it really just comes from this. Yeah.
Just replace D with the diagonal matrix with B in the diagonal.
Exactly. So let's define, let's say, F1 to be the matrix that has just says diagonal entries, or I can even this Fj is a matrix with diagonal entries dj1 all the way through, let's say, dj. So now I'm in trouble because I called the dimension D. So that's going to look nasty, but let's just call it R. Supposing these were R by R matrices. OK, and I made all the other entries 0. And I did the same thing for F0. I defined it to contain the diagonal entries of this vector. Then now you can assure yourself this is true. Matrix inequalities on diagonal matrices are the same thing as the inequalities component-wise. Okay, it's because the eigenvalues of diagonal matrices are the diagonal entries. So it reduces to what you know already, the kind of usual component-wise inequality you know already. Great. So now we know that we can turn any LP into an SDP, although we wouldn't probably want to do that. We just are seeing the hierarchy. OK. Standard form for SDPs is a bit of a jump. So LPs and QPs, you guys like nodding your head like, yeah, standard form. It looks marginally different from the other form, and the proof is just involving slack variables. Standard form for LPs looks pretty different. And when I was first learning this stuff, I was always confused about it, because the standard form involves a matrix variable, no longer Euclidean variable, like x here is an Rn, x here is a matrix. Okay, so standard form for SDPs in this form, they at least transparently appear quite different. But the nice thing is that both of them have very close ties to their LP analogs. So you can easily remember both of them. Right, this one we just saw the tie to LPs through this argument right here. Take a look at this form of SDPs. I've basically taken my standard form LP and I've replaced all the inner products with matrix inner products and all the inequalities with matrix inequalities. And I've just gotten the exact same thing. So C is a matrix. So instead of C transpose X, where C and X are both vectors, I have C dot X, where C and X are both matrices. Instead of having AI transpose X is equal to BI, which is one row of the constraint, AX equals B, I've replaced that row with a matrix, and now I have AI dot X equals BI. And I've replaced X bigger than or equal to 0 component-wise with X is positive semi-definite. So it's just all the matrix analogs of the standard form LP, of the lines in the standard form LP, of each of the different quantities. So I'm thinking we might put this on the homework, or if we don't, then we may come back to it in a review or something like that. But I would start thinking about why any semi-definite program can be written in standard form. It may pop up on your homework. It's not as easy as introducing slack variables, but it's also not terribly hard. You can kind of see, probably, how to go from this to this. You use the argument that was just given earlier, which is that you make capital X to be a diagonal matrix with just this X on the diagonal. And you can kind of work everything in that form. And then you have a bunch of linear equality constraints that enforce the off-diagonal elements of this X to be 0, so that it really is a diagonal matrix. The other way around, you just unravel everything here as if they were vectors. So you write C dot X as if C was some super long vector, and you unravel the matrix X as if it was some super long vector. And you do the same thing for these constraints. And for this, how do you write that in terms of inequality of this form? What's that? Yeah, so each of these Fs is just going to be a matrix that picks out one particular component of X, right? So we're going to get that full semi-definite inequality. But write that out, or at least you can start thinking about that. That might be a homework question. So don't be startled, by the way. This is the point of this. If you see SDPs written like this or like this, because they're equivalent, even though they may look different. So some examples of SDPs. One very nice example, which I myself was not super familiar with, but Javier used it as an example last year when he taught this guest lecture, is the Lovasz theta function. And it has a bunch of connections to graph theory as well. So you might have seen this in a CS theory course if that's something that you've taken. But it's a pretty remarkable paper written by Lovasz in 1979. So if you have an undirected graph, G, with, let's say, nodes N and edges E, and you define these two graph theoretic quantities, which is omega G and chi of G, which is the clique number and the chromatic number of G. So how many people have heard of these quantities? I'm just kind of curious. Oh, I thought we had some SCS folks in here. Maybe everyone from SCS is being lazy and watching on YouTube. So I won't go over this very carefully then. I thought it might be interesting to some subset of the class. I'll just say what it is. But the clique number of a graph is the size of the largest clique in the graph. And the chromatic number is the smallest number of colors you can use to color the graph so that no two nodes that are adjacent have the same color. Both of these quantities are NP hard to compute. So you can't really compute them. They're just graph theoretic quantities that people are interested in knowing because they describe kind of properties of the graph. They're kind of characteristics of the graph. The Lovasz theta function is defined as the solution to a particular SDP. Amazingly, this lies in between those two NP hard to compute numbers. So this is what Lovasz proved in 1979, that if you want to get some sense of the clique number or the chromatic number, you could actually solve this SDP and get something that's sandwiched in between those two quantities that might be hard to compute. And that SDP is rather simple. It's just, look, this is just the sum of the entries of x. That's what the criterion is, subject to this very simple equality constraint on x. The identity times x is equal to 1. And x has to have all its off-diagonal entries equal to 0. No, not off-diagonal, excuse me. All of the entries of x that do not correspond to an edge have to be equal to 0, and x has to be positive semi-definite. So if you solve that SDP, then you get what's called the Lovasz theta function. And Lovash's sandwich theorem tells you that it lies in between the chromatic number and the clique number actually of the dual graph or the complement graph of G. OK. That was very fast. We're not going to see that again in the class. I just wanted to bring it up because I thought it was interesting.
What is the y1?
1 is a vector of all ones. So 1, 1, t. Sometimes I'll write that with calligraphic ones. Yeah, this means the matrix of all ones. Just the outer product of the one vector with itself. OK. A more relevant, in a sense, to this class at least, SDP, is the trace norm minimization problem. So this is the analog to the sparse linear system problem we talked about at the start, but for matrices. OK, so now I'm trying to find the solution to a linear, a system of linear matrix inequalities that's low rank. If all the matrices were diagonal, then this would be the same thing as finding a sparse solution to a linear system of equations in vectors. It's just a generalization of that idea. And we'll revisit this when we talk about matrix completion, maybe in 3 or 4 lectures from now. But this is an SDP. That was our way of introducing it. This is an SDP. So first, let's talk about what it means to have a system of linear matrix equalities. We're going to think about a linear map applied to a matrix, so script A of x, as just something that takes a matrix and gives you back a vector. And in each component of that vector, you're looking at the inner product of a particular matrix with x. So if you thought about how a matrix operates on a vector, it's really the analogy here, right? These would be like the rows of the matrix transpose x, but now we're in matrix world. So I'm taking the inner product of a matrix transpose x in each component. So given, say, a linear system of matrix equalities, script ax equals b, let's suppose we want to find the lowest rank solution to that set of equalities. And as we saw before, the rank function is very non-convex. So this is not a convex problem. The trace norm approximation to it, which again I'll just say once more, is the analogy of replacing the L1 norm with the L0 norm, replacing the L0 norm with the L1 norm, but for matrices, is to swap out the rank for the trace, which is the sum of the singular values of x. We learned that norm last time. Just remind you, the trace of x is the sum of the singular values of x. So we write singular values usually as sigma I of x and eigenvalues as lambda I of x. Here x need not be square, so that's why I'm using singular values. OK, this is an SDP. It's actually quite intricate to show this. And I'm not sure that it's going to be very eye-opening to see it, but it might be something, again, that we put on a homework. I'll just tell you what the kind of flow is of the proof. You can always rewrite a norm in terms of its dual norm. So any norm I can write as the maximum inner product of a vector. So this is an equivalence we'll see when we talk about duality. If I have any norm, I can always write this norm as the maximum inner product I can achieve with x over all vectors y that have dual norm less than or equal to 1. So there's a unique norm that's called the dual of my norm, and this is actually the way to define the dual norm. So that's the way I can express a norm. And it turns out that the trace norm is actually the dual to the operator norm. So the trace norm, which is the sum of the singular values, its dual is the operator norm, which is the largest singular value. Okay. Again, if we make the analogy to Euclidean norms, this is like the L1 norm, which is the sum of absolute values. The L1 norm is dual to the infinity norm, which is the largest absolute value. So it's really a very tight analogy. Trace norm is dual to the operator norm. Therefore, I can rewrite this problem as the minimum over x as the maximum over y of y dot x for all y that have operator norm less than or equal to 1. And the set of y's that have operator norm less than or equal to 1, I can actually turn into a semi-definite constraint. That just involves a little bit of massaging. So that's how this is an SDP.
Does this mean that we need to write the dual problem to show that there's a
No, we're not writing a dual. We're just actually using duality of norms. We would just use this. The trace norm of x is the maximum over all over all y that have operator norm less than or equal to 1. So this means that the singular value, the largest singular value of y is less than or equal to 1 of y dot x. We would introduce this variable, and then we would rewrite the constraint on y having operator norm less than or equal to 1 in terms of a semi-definite constraint. I'm actually not sure I would put that on the homework just because it doesn't really, I mean, it's specific to this problem, this manipulation. But if you're interested in seeing it, you can come to my office hours. I can show you the rest of the proof. OK. Now we have about just enough time to finish the rest of the hierarchy. Yeah, question?
So is the operator norm always the maximum singular value?
That's how we define it, yeah. Kevin?
Do you need this type of trick to show that SOCPs are SDPs?
Close to it. We have that here. So we'll get to it in a few slides. We have just enough time to finish the rest of the hierarchy. So conic programs are the most general form of problems. And if you had an amazing solver for cone problems, then you'd be a very popular guy. Because almost every problem anybody ever wants to solve is a cone problem. And so, like I said, CVX and all these other general purpose solvers are all built on top of cone problems. Cone problems, they just take the linear inequality constraint, say dx less than or equal to d, and they actually just take that less than or equal to sign and they replace it with a conic less than or equal to. And what the Boyd and Vandenberg textbook does is it defines a bunch of partial orderings over cones and introduces like a new notation for less than or equal to, but for cones. I think that's a little bit confusing. So the way to think about it, I think, is just you have a cone k that you like, a convex cone, and you're enforcing the constraint that dx plus d has to be in that cone. That's all a cone problem represents in place of the dx is less than or equal to d. So if this cone, if k was the non-negative orthant, then this would say that dx plus d has to be bigger than or equal to 0 in every component. That would give you back the LP. Okay, it's just a component-wise inequality on dx plus d. Instead of the non-negative orthant, if we took the positive semi-definite cone, we'd get back SDPs. Because we were saying that dx has to be bigger than or equal to d in a matrix sense. Okay, and here I would think about x and d as matrices rather than as vectors. The lowercase x and d. Yeah. I'm sorry? This statement? I mean, it's true for every norm in the sense that every norm has a dual norm that makes this true. Sorry? Yeah, it has to be a proper norm. But every norm is going to have a dual norm that makes this true. That's how we define the dual norm. OK, so cone problems are more general than SDPs and LPs because we saw we could recover SDPs and LPs just with two different choices of cones. And they can get much more glorious or terrifying depending on your perspective as you choose different kind of funky cones. A specific type of cone problem that's an interesting one is called the second order cone program. And let me draw that in our hierarchy so you can just get a sense for where that lies. This is what we're going to show in the next few slides. And if you forget everything from today's lecture and all you remember is this picture, then that's at least that's something. Just remember this picture. So second order cone problems lie in between QPs and SDPs. So that's how we're going to actually prove that a QP is an SDP. We haven't shown that yet. So a second order cone problem is an optimization problem where we actually choose as K here the second order cone, or the Lorentz cone. Remember we said that is a, it's the set of all pairs xt where x is a vector and t is a scalar such that the L2 norm of x is less than or equal to t. Remember that gave us that the ice cream cone shape, for example, if we saw x as a vector in R2. This actually corresponds to taking K to be the Cartesian product of a bunch of different second order cones. That's how you can see that this is a cone problem. But this particular problem is a cone problem as we've defined in the last slide. But the general form is that, again, I have the usual criterion and equality constraints. My inequality constraints are that the L2 norm of some affine function, some matrix di times x plus vector di in L2 norm, is less than or equal to some other affine function. Okay, so that's a second order cone program. And you'll see a bunch of examples in Boyd and Vandenberg about how people use second order cone problems. Turns out you can write some various types of covering problems, like minimum volume inscribing ellipse or something like that as a second order cone problem. But for our purposes, why I wanted to show it now is that we're going to use it to serve as the link between QPs and SDPs. And we're going to do that in a couple of steps. Yeah?
In the previous slide, you had mention of an EI. You're not talking about a standard basis vector, right? You're just talking about a random.
Sorry, EI is just an arbitrary vector. Yeah. Yeah, it's not the standard basis vector. So the first thing we're going to do is realize that every second order cone problem is an SDP. And to do that, we're going to use a little trick from the Schur complement theorem. And I'm going to claim that, that this is true, that x having L2 norm less than or equal to t is equivalent to the following matrix being positive semi-definite. The matrix T times the identity in the top left block, the vector X running down the columns, and then the last row is going to be X transpose in T. So I claim that these two statements are equivalent so that I could think about now having a matrix variable and having a semi-definite constraint on the variable. This actually follows from the Schur complement theorem. So the Schur complement theorem is a handy thing to know if you're dealing with problems of these forms. Says that if you have a block matrix of the form A, B, B transpose C, then provided that C is invertible, this matrix, this block matrix, is itself positive semi-definite if and only if the Schur complement form is positive semi-definite. And that Schur complement form is this, A minus B, C inverse B transpose. So you can actually see this just from like a block matrix manipulation. You can write out what this means and get to that equivalence. So let's apply this fact from linear algebra to this. We just see that Ti x x transpose T is positive semi-definite, right? If T is bigger than 0, that's what C to be invertible means. If and only if the Schur complement is positive semi-definite. So that looks like this, Ti minus x x transpose over T positive semi-definite. And I can also rewrite that as, right, just T squared I minus x x transpose is positive semi-definite. And now you can see that this actually exactly reduces to saying that the norm of x squared has to be less than or equal to t squared, because this guy is rank 1 and only has one eigenvector, and that's x, and it only has one eigenvalue, and that's the norm of x squared. So this is equivalent to saying that that's true. Because this one works. OK, so with this transformation, hopefully now you'll believe me that every SOCP is an SDP. And I'm like a minute over time, but I'm just going to tell you that every QP is an SOCP. So we may or may not just come back to this and do this last time. Maybe we'll just kind of skip it, and I can let you guys check that. But it provides us the link between QPs and SDPs, which gives us this picture, the one we saw at the start of the class. So like I said, remember that picture, put it on your office wall or something. It's nice to have as the hierarchy of all the problems that we're going to solve in this class.